Alrighty, so we are in Unit 3, Lesson 1, which is going to be the definition of a derivative, and the whole last unit we devoted to limits. So we're going to start out by talking about limits. Limits are going to kind of introduce the concept abstractly, and then we're going to move into this more algebraic understanding of derivatives. So if we look up top, let me see if I can zoom in a little bit more just so we can see this, okay? This is something we've been talking about that has to do with average velocity versus instantaneous velocity, okay? So if I pick 2 points on the line, let me see if I can readjust slightly, okay? So if I pick points P and Q, this is what we would call a secant line that connects those 2 points. Secant lines were average velocity. So that's when we would simply find the slope between the two values. So we would come over here, we would come over here, we would find this would be like f of p, f of a. This one would be f of x, correct? Because the values, these are the input values down here. And then we would plug in, these would be the corresponding y values, and we would say like f of x minus f of a over x minus a. Yes? Everybody's with me with that? All right, and then what we said is that the truth is if we were really focusing on P, and we draw in this kind of pink line, that is going to be your tangent line. And as we look across, this is what's happening that's changing, as Q gets closer and closer to point P, in other words, X, which is down here on the bottom, is getting closer and closer to A, the slope that we calculate gets closer and closer to what the slope of the tangent line is. And in terms of tangent lines and questions that could be asked of you, the tangent line, which is the pink line, we also called instantaneous velocity or instantaneous rate of change. So average velocity or average rate of change early on, that was the very first lesson in the last unit. All right, so this graph is just kind of a connection to what we did before, that we have this situation with P and Q. As Q gets closer and closer to P, the averages start to really approximate what the instantaneous rate of change is at point P. All right, that's our idea behind this. This is like the context of what we're doing. All right, so if we draw here, so this is where we're going to take the information we did and we're going to move it into this new limit definition analysis. And we just draw this curve that comes up through, and we pick 2 points on the line, and we say this is A, and this is X. And then over here, that makes this f of A, and this makes this f of X. We know that the slope between those, again, was f of x minus f of a, which is what I said out loud, and now we're writing in math terms, is equal to x minus a. Y minus y over x minus x. We're just using function notation now. Okay. And the new part is this. The new part is going to be this symbol, f prime of a. F prime is a way that we refer to what is the derivative. So here are your words you can substitute. Derivative is equal to the slope of the tangent line. It's the instantaneous ROC, or it's the instantaneous velocity, depending on the application. All 4 of those things are talking about f prime of a. So if you remember, a limit was, well, what is the y value approaching? The tricky part of this, which is what we're going to be using today, okay, so I'm going to put a blue box around this and call it equation 2. Okay, and I understand that it's first, meaning we talked about it first on the left, but you'll see we don't use this one as often, but this is what we can build off of to understand the lesson. So when we look at the derivative at A, what is the slope of the tangent line at A? What we're saying is, and I'm going to switch back up top here, if we can calculate the slopes of all of these secant lines over and over and over and over and over, as x gets, notice, closer and closer to A, so x is approaching A, so it's getting closer and closer up here, so take a look, x is moving closer and closer to A. As that interval gets smaller and smaller and smaller, it approximates the actual instantaneous ROC, or the slope of the tangent line. So in math language, that's where limits can be used to explain that phenomenon. So this is our definition, limits. Now, most of you see limits as input and output. Okay? Please recognize this is a rational function. So if whatever a is, when I plug it in for x, if it gives me a 0, I can't find the limit. Okay? This is our very first equation that we can talk about and deal with. All right? So, moving over here to the right, so I'm going to zoom out a little just so we can see this side by side. Moving over here to the right, we're going to use function notation to grow this up a little bit more. Okay? So here's what I mean by that. I'm going to use that same exact curve coming across here to here. Okay? This is still going to be a, but now I'm going to define this not as a single variable x. I'm going to define it as the quantity, whatever a is, plus some distance h. A plus h. If I use my same function notation, this is f of a. Coming across here, this is going to be f of a plus h. The slope here is going to be f of a plus h, the y value minus the y value, over a plus h minus a. If we simplify this, so this simplifies, we get f of a plus h minus f of a, all of which is just over h. So recall over here, this is my secant line. This is my tangent line. This is my secant line. This is my tangent line. Right. So now, using the same concept of limit, the players are different. What I'm inputting for the input value along the x-axis is different. But notice, I still have this new notation, f prime of a, but now I have this new limit based on that diagram that I'm going to call equation 1. So I think it makes sense, as h goes to 0, this a plus h is going to get closer and closer and closer to the actual a value because you're adding smaller and smaller increments. That's what we're doing there. All right, so I want you to take a second and read through the statement that's here about a tangent line. A tangent line, y equals f of x, at this point, is a line with the following equation. And we're going to break that statement down. Take it, read through it. You need to practice reading the math language on your own, seeing if you understand it. And then we're going to connect it to what we already know. All right, here we go. So, point slope form. Y minus y1 is equal to m times x minus x1. That you should have seen before, okay? Where y1 and x1 are the x and the y of the one point we know on the line, and m is going to be slope. Okay? So now, if I take the information, I want a tangent line that we're referring to as f of x. So I have this xy axis. I have a curve that comes across. I've got this and this that's here. Okay? So this is my point A. Here's my tangent line. So this is going to be f of A. Right? What you see right here that I've just drawn is all of this information here. So this is f of x, the line, the curve rather. Okay? So this is me taking what it says here and thinking about it graphically. So when I look at this, I'm like, okay, not a big deal. A goes in for x1, right? Isn't this ordered pair located at A, comma, f of A? So I have y minus y1, y minus, so my y1 is f of A, is equal to, we'll leave this open for right now, x minus A. Now, the whole idea of this lesson, and this is why it's so important that we start to connect this idea moving forward, is that I use this here, f prime of A. Every time you see f prime, you should think in your mind that is the slope at a point on the curve. Which point? In this case, the tangent point that I drew right here. So that's why we're saying this is f prime of x. Put a little f prime there. Let me make that a little easier to see. F prime of x. Because this is the slope of the tangent line. Right now, we only know two ways to find that slope, or instantaneous rate of change. We can either use this blue limit or this green limit. This is the calculus of finding the slope. Okay? That's where we are right now with our introduction.